Welcome back. So in the previous few videos we have been discussing the Fourier analysis of continuous time signals. We did the Fourier series for which was for periodic signals, and for non-periodic we had the Fourier transform. Although we can also apply Fourier transform to the periodic signals, there is no such restriction. And in this course we are mainly interested in the frequency analysis of the continuous time signal. So we did an in-depth analysis. Now we'll do the discrete time, the Fourier analysis. That's Fourier analysis for the discrete time signals. But again, we won't be doing an in-depth analysis because you have a separate course for discrete time signals in your 6th or 7th semester. That's digital signal processing. But the formal analysis we will done here, and you will see that there will be a lot of similarity, of course, with some small minor differences that I will point out. But there will be a lot of similarity between the analysis, the way we present the Fourier series, or for that matter, the Fourier transform, when compared to the what you call the continuous time cases. So we'll have a similar kind of analysis. There may be small differences that we will point out. So in this video, we'll be starting with the first case, that is the case of what you call periodic discrete time signals. Fine. For which we have, of course, the discrete time Fourier series. Fine. Now discrete time signals, we know that the periodicity property is something like this, that you have a sequence x of n, and if it is periodic, we represent it like this, where capital N is the time period, and the smallest positive value of n is going to be an integer. This is the discrete time case, so we are dealing only with the integer values, and the smallest positive integer n, it will be over the fundamental period, and corresponding to that fundamental period you will have the fundamental frequency, which will be related like this. This thing we have done in our first chapter when we discussed the periodicity. Now in Fourier analysis, we try to express our signals in terms of complex exponentials. That was the approach we followed in continuous time case, and same approach we're going to follow in the discrete time case. So again, we know the basic complex exponential in what you call discrete time, something like this, j omega naught n. Yeah, if you express it in terms of the fundamental period, we can say e raised power j 2 pi by n. Now this is periodic, this signal is periodic with period n, capital N. Fine, this we know. Now we will define a set of exactly same way we did it in continuous time case. So we will define a set of what you call discrete time complex exponentials that are related, harmonically related. Exponential that are harmonically related, yeah, we can say that are periodic with period n. Fine. So I'm defining a general kind of an exponential phi subscript k n as an exponential of this kind j k omega naught n. Fine. Yeah, if you express it in terms of what you call time period, it can be like this. And of course k, it is going to be integer, which means all the quantities in this expression, whether it is small n, capital N, and now this k factor k, which will define different exponentials, they're going to be integers. Fine. And these, you give different values of k, phi 0 and phi 1, and you will get different exponentials, and those exponentials will be harmonically related in the sense that they all have the same time period, and here you can say the same frequency, 2 pi by n. Fine. Now there is an important, we use, if you remember, if you can go, if I go back to the continuous time case, I have it here. We used a similar kind of analysis where we defined this thing, e raised power j k omega naught t. But there is one fundamental difference between the continuous time case and the discrete time case, is that these signals that we are generating phi k or t, they have certain periodicity. In the continuous time case, like I said here, you define the signal phi k t, then for different values of k, you could have different exponentials, right? So if I define, let's, for just for sake of understanding, if I define phi 0 n, it was e raised power 0, which is 1. Then I define, if I define phi capital N, it will be e raised power j capital N omega naught n. Fine. And which will be e raised power j capital N omega naught n equivalent 2 by n. Then this and this will go, it will be e raised power j 2 pi n, which is again equivalent to unity. Fine. Then if I define phi 1 n, it will be e raised power j omega naught n. Then again, if I define phi capital N plus 1, it will be e raised power j n plus 1 omega naught n, which will be e raised power j omega naught n into e raised power j n omega naught n, which again will be e raised power j omega naught n, and this thing, it will be unity. So there's a kind of pattern where we see that phi of 0 n is the same as phi of capital N, and phi of 1 n is equivalent to phi of n plus 1 n. Fine. And likewise, for example, next phi of 2 n, if you do this simple substitution, it will be equivalent to n plus 2 n. Fine. So it turns out that in the discrete time case, for distinct values of omega, the set of exponentials that we have defined using this, they will repeat themselves. Fine. So if we start with phi 0, phi 1, phi 2, phi 3, phi 4, whatever the time period capital N is, then they will repeat. Fine. So it is something like this. You have a set of exponentials, let's suppose phi 0 n, phi 1 n, phi 2 n, and if we suppose that time period n has a value of 3, then what will happen? Phi 3 n, इसके बाद you will have phi 4 n, yeah, since n is 3, so 1 2 3, phi 3 n, it will be the same as phi 0 n. तो जो आपका next होगा phi 4 n, it will be the same as phi 1 n, and so on. So in general, I can say that phi k n, it will be the same as phi k plus r n. That means the set of exponentials that we are defining using this phi of kn, they will repeat themselves. and the period of repetition will actually be the time period n. Fine, this is an important one. Continuous time as an ether. So if you had a continuous time representation, phi kt is equal to e raised power k j omega naught t, you gave different values of k, and you could have, I mean, theoretically infinite exponentials which were different. But the thing is, for discrete time case, with this general kind of an expression, you will have exponentials that will repeat in value after the time period n. Fine. So when k is changed by n integer which is multiple of n, you will have identical sequences generated, right? Which, like I said, it differs from the continuous time case in which the signal phi of k of t, they were different from one another. Fine. So this is an important property. Now if I define my signal, if I define a sequence, a signal x of n as a summation of these, I can say as a linear combination of these sequences that we just defined, phi kn, it will be summation k a of k e raised power j k omega naught n. But again, owing to this property that these exponentials, they repeat themselves, this summation will be over n samples, yeah, over n such exponentials. Unlike in the continuous time case where the summation, if you go back, it will be over infinite, from minus infinity to plus infinity. Let me see if it is here. Here, from minus infinity to plus infinity. The reason being a continuous time case may the exponentials which we defined generally using phi of k of t, they were different for different values of k. But since here the exponentials are repeating and they are repeating after an interval equivalent to multiple of n, so जो आपका summation होगा या जो the expression of your signal x of n as a linear combination of these exponentials, it will be over a period of n being the time period. Fine. So this will be the Fourier representation of our discrete time sequence. So we have x of n. If it's a periodic signal, it can be expressed using the exponentials over the time period capital N. Fine. And then coefficients के लिए we have the same expression, 1 by n being the time period, again over the period n, x of n e raised power minus j k omega naught n. Fine. So again, this we call the synthesis equation, and this we call the analysis equation. And as you can see, there's a lot of similarity between these two expressions and the expressions we had for the continuous time case. Like I said, we won't be doing the in-depth, although we used this, we kind of did the same kind of analysis that we did in the continuous time case. Okay, so before we proceed, let's do a simple example. Although, like I said, you will have a separate course for the discrete time in the 6th or 7th semester. That will be your digital signal processing. But just for the sake of continuity, let's try to have a signal x of n sine omega naught n, and let's try to have its, what you call, the Fourier series representation. Now, Fourier series applies only for periodic signals, and from our first chapter we know that we have to check the condition for periodicity before we can conclude whether this is a periodic signal or not, right? Unlike the continuous time case, jahan pe if it's a sinusoidal signal, it is a periodic signal. For discrete time case, we have to check, and for checking, we have to basically ensure that omega naught, say n, must be equivalent to 2 pi m, where n and m are integers. And I can say that if I arrange it slightly, 2 pi by omega naught is equivalent to capital N by small m. Now this is the ratio of two integers. Now a ratio of two integers, it can either be a ratio or it can be another integer, say n tilde. Like for example, n is 6, m is 2, 6 by 2 is 3, which is a pure integer. But then there can be a case where you can't resolve the ratio. For example, 7 by 3, you can't have an integer for that. So let's first assume that, so okay, for this case, so for x of n to be periodic, 2 pi by omega naught, it can be an integer like in this case, or a ratio of integers. Fine. So for the case where this 2 pi by omega naught is an integer, say कुछ भी n या n tilde, fine, then उस केस में omega naught will be equivalent to 2 pi by this value n tilde, and आपका जो x of n है, you can express it as, since the sine function, you can use the Euler's theorem. The Euler's relation will be 1 by 2 j e raised power j 2 pi by n tilde and minus 1 by 2 j e raised power minus j 2 pi by n tilde n. Then if you compare this expansion with the general form, we will get that जो हमारे coefficients है a of 1, it will be equal to 1 by 2j, and a of minus 1 will be equal to minus 1 by 2j, and the remaining coefficients over the interval of summation, yeah, over the period n, they will be 0. Fine. So if we have that हमारा period is n tilde, so it will have some integer value. So within this integer, for example, if n tilde is 5, so you will have from minus 2 to plus 2. Out of these, so it means you will have coefficients a minus 2, a minus 1, a0, a1 and a2. Now out of these, a1 and a minus 1 are defined, and rest of these three coefficients, they are 0. And then the coefficients will repeat. So if this is a1, this is also equivalent to a n plus 1 because of that property. And if this is a minus 1, then a n minus 1 is also equivalent to minus 1 by 2j. In case where it is a ratio of integers, so if 2 pi by omega naught is a ratio of integers, that is n by m, so accordingly your relation will vary. So x of n, it will be equivalent to 1 by 2j e raised power j m 2 pi by n minus 1 by 2j e raised power minus j m 2 pi by n. And again, if you compare, so your mth coefficient a subscript m will be 1 by 2j, and a minus m will be minus 1 by 2j, because here period is not defined. It is defined, but it is a ratio of these two things. So important thing here is that the analysis is quite similar to the one we did in continuous time case, but there is a thing that these complex exponentials, which are harmonically related, they will be repeating themselves after the interval, which is equivalent to time period. So we'll stop here, and next video will take the non-periodic signals for the discrete time case.